have some sphere of radius r, then you have cubic divergence, and also you have linear divergence in lambda. So this is UV scale. And also you have a finite part, so which I will call, I think in my notation, if I define this in this way, and then the finite part becomes f. Okay, I have already renormalized my partial function to define the f. So you can cancel these terms by adding a counter term, local counter terms. Okay, so I'd like to show somehow prove this conjecture, but somehow want to use the properties of entanglement entropy. So how are they related? So for CFT3, so if you remember my previous talk then, so I consider the CFT, and also I computed the entanglement entropy of a disk of radius r. And then the disk entanglement entropy actually is given by minus f, or more precisely, log of the three-sphere Gaussian function. Okay, if you, yeah. So I showed you this equality before, but here, actually I was using unrenormalized Gaussian function. So in general, you have a UV divergence. So if you translate this result with three-sphere Gaussian function, then you see that, okay, the entanglement entropy of a disk, it has a UV divergent part, which is proportional to the area of my region. So I have a disk of radius r. This is r. So I always have entanglement entropy always have areal divergence. So here you have areal divergence, and the finite part should be minus f, because entanglement entropy is equal to log of the partial function. So this is areal part. Okay, so then you see that the entanglement entropy and the free energy on three spheres are related with each other. So you can somehow come up with nice interpreting function between FUV and FIR by using entanglement entropy, similarly to the two-dimensional case. Okay, so I will going to define a function, interpreting function between FUV and FIR. So to prove the XRM, so I need a function, the script f, which is a function of r, radius. I will define it in a minute, but I have to have some function which coincides with the three-sphere Gaussian function, sorry, three-sphere free energy for CFT, and also I have to prove that the derivative of script f is non-positive. So I need such a function. Actually, you can find such a function using the entanglement entropy. And that function is called the renormalized entanglement entropy. So I will define a renormalized entanglement entropy. And this was introduced by Liu and Metsui 2 years ago. So basically, so since the entanglement entropy has the areal divergence, so we have to somehow cancel this part. So to cancel that part, the minimal way is that define, so act some derivative operator which cancels the areal divergence. So here S of R is, so this is the entanglement entropy over this. Okay? So I define such a function. So if we add this operator, differential operator, to this guy, then the areal part cancels, goes away. Okay? So this function satisfies the first property. Okay? So f of R for CFT3 is equal to just the f. Right? So this guy cancels the first part, but so this guy cancels f, but this doesn't. So you get f. Okay. So this is satisfy the first properties, and I'd like to show you the second properties, but the proof is very complicated. So I just mentioned that. So to prove the second property, so you again have to use the strong subjectivity and plus Lorentz invariance. Obvious theory. And then, so somehow you can prove the second properties. So this was also done by Kashin and Furuta. So basically, in 2+1 dimension, you use a boosted disk, a boosted circle, and but you have to prepare infinite numbers of boosted circles, and by combining the strong subjectivities for boosted circles, you can prove the second property. So proof is very complicated, so I will show you. Okay, is there any questions so far?
So again, you have two functions that are both monotonously decreasing along the RG flow.
In
Just
3
like
dimension?
in 2D.
No, I only have one function.
So this will be the same, on the CFT. Okay.
Yeah. Okay. Here, so excuse me. So f is only defined for CFT.
So can I ask a denied question? That what does it mean when you have two functions in 2D that monotonically? I mean, originally the point was that there's a measure of the degrees of freedom, but now you have two functions and they both satisfy what.
Yeah, in 2 dimensions, so you have two different types of functions. Both satisfies a requirement of the measure of degrees of freedom.
Right.
Yes.
So then it's not unique anymore. So.
Yeah, it doesn't have to be unique. Yeah, as long as it satisfies the monotonicity and also it coincides. Yeah, as long as it is monotonically decreasing along the RG flow, then it can be a measure of degrees of freedom.
But not absolute flow. There's no sense of absolute.
Yeah, but I thought there was, ideally when we look for a function with a nice property that the RG flow would be the gradient flow with regular function.
Right.
This is not available.
This is not. Yeah, this is not. Right. So the difference between the Zamorsky C function and the entropic C function in 2 dimensions is that the Zamorsky C function is always stationary. So if you take a derivative with respect to the relevant coupling, so then this is proportional to the beta function. So it guarantees that the Zamorsky C function is always stationary.
I think that statement is only true to first order conformal perturbation theory. It's not true at generic point along RG flow.
Yeah.
So even the Zamorsky function doesn't quite have the right property to such that its gradient flow agrees with RG flow. It's only true approximately near the fixed point.
Right, near the fixed point. Yeah, near the fixed point. So in this sense, yeah, they have very different properties. So you can use whatever you want. So depending on
Can you achieve that by doing linear combinations?
Linear combinations. Yeah, you can use a linear combination of them.
guess you only really compare at the fixed points, right? You're not comparing. But you are really calculating those at the fixed point. You don't worry about what's going on in the middle.
It's much better if you also know what's going on in the middle.
Yeah, well,
Yeah, but anyway, so to prove such a theorem, so you need an interpolating function, right?
So in the free theory in two dimensions, you are able to compute the interpolating.
Yes, for
for
massive scalar and for massive fermions, you can compute exactly the entropy C functions.
So can you say something which C function is closer to the actual number of degrees of freedom?
So once you have interaction, it's not clear how to define the degrees of freedom. Yeah. For free theory, you can count the number of fields in the Lagrangian, but if you don't have any Lagrangian description, then it's not clear, at least to me, how to count the numbers. So in QCD, so you have mesons as a bound state, and it depends on you, so how to count the one meson. Right? So meson can be 1 degree of freedom, or maybe 2 because it's made of 2 quarks. Right? So once you have interaction, the definition of the definition of the degrees of freedom is ambiguous. So that's why we need a mathematically rigorous function, which Montague degrees is. Okay, so since the proof is technical and I skipped the details, so I'd like to show you an example. So where you can compute this guy, so we normalize the entanglement entropy. So I'm going to, so to this end, I'm going to focus on the entanglement entropy in a gap system. Gap space in 3 dimensions. So here I have a mass gap and M, so M is gap scale. And I let it be very large. So then, so you have a region A. And so this is the boundary. So this is the entanglement surface, the sigma. So then entanglement entropy always have a area of divergence. So L sigma is the area of A. This is the area of A. So you have an area of divergence. But here I'm interested in the gap system where mass gap is very large. So I expect that the entanglement entropy can be expanded in terms of the inverse of the mass. So the most general form of the entanglement entropy is as follows. So you have linear term in M and also some constant term. I will call gamma. And here you have expansions with respect to the mass gap. Okay, so this is the general form. So here, so gamma is so-called topological entanglement entropy. And if there is no mass gap, we have this part and only the topological entanglement entropy for 3 sphere. So gamma is just the free energy on 3 sphere. But now we have a mass gap, so we expand it like this. So this is the general form. And
so this area is of arbitrary shape, or?
Yeah, here, A is have some general shape.
And the coefficients, will that depend on the shape?
Yeah, coefficient depends on the shape.
Okay.
Thank you so much. Yeah. So since now I assume that the M is very large, so then the correlation length is very small, very short. So the entanglement comes from only the near the entanglement surface. So we expect that this coefficient C, so this C can be written as a function, so integral of some function of the exit curvature. So kappa is the exit curvature for sigma. So this is exit curvature. And we expect that C, this coefficient, is given by an integral over sigma, not on A, but sigma. Since this is the correlation length, and the correlation length is very small, so we expect that the physically entanglement comes from the region near sigma. So, but I'd like to confirm this claim. Okay.
The function f is undetermined so far?
Undetermined, yeah. This is unknown function.
But it's universal? Does it depend on what theory you're considering?
I think it depends on your theory.
Depends on?
Yes.
Okay.
And also, so one property, so one general property of that function
Where's
is
the L dependence? L dependence.
L.
On the left hand side you have.
Oh, right. So this is also a function of L. Yes, thank you. So since the entanglement entropy of region A is equal to the entanglement entropy of its complement, so okay, so this is one of the properties of the entanglement entropy. So it follows that f is an even function. This is an even function, FL. So you can flip the sign of kappa inside F.
This is why only odd powers of m show up?
Right, exactly. Thank you. Okay, so F should be even because so kappa changes the sign. So when you measure kappa from outside or inside, okay, it depends on the normal vector of sigma. So this is normal vector. Okay, is it clear?
By F you mean there is no higher derivative on K on extrinsic?
Actually, there is a derivative with respect to some derivative
On curvature.
on curvature. Yeah. In general, you have a function. So f is a function of kappa and its derivatives. Some derivative of kappa,
Okay.
Yeah. But here, the form of the function is not known, so I'd like to focus on an example. So massive scalar or massive fermion. Okay, so this is kind of technical, but yeah. So I'm going to compute the script F. So we normalize the entanglement entropy for gap system, and show you that F actually decreases monotonically. So when M is very large.
So just make sure I understand. In the case when this is a disk, this is agrees with this three-sphere Fourier function, and all these kappas is constant, so these are just some fixed numbers.
Actually, for three-sphere case, let me see. Okay, if you have a conformal field series, then gamma is just F.
Yes, but when you're considering the gapped.
For gapped case,
Yeah.
in general, SA is no longer equal to F. I mean,
Oh, well, you say it's not.
right. They are different quantities.
I see.
Right.
Right.
F is only defined on three sphere.
Okay.
Right. So I'm gonna fix the first coefficient, C minus 1, in my notation. I'm gonna fix C minus 1 for free fields. And so this is based on my paper with Igor and Sylvie. Okay. Anyway, so to fix the coefficient, I like to start with 4-dimensional field series, so not 3-dimension. So I like to start with the theory in 1 dimension higher. And okay, so this is my third direction, so x4, and I compactify one of the direction to the circle of length L, and then here this slice becomes R2. Sorry, I forget about the time direction. So this slice is supposed to be R2. And here I have my region A. But I extend this region into the 4-dimensional direction. Okay. So here I have some cylinder-like geometry, but actually I identified both directions. Okay, so this is S1. So what I'm doing is that I start with 4-dimensional field series, but one direction is compactified, and I will get 3-dimensional field series in the end. So since if you start with massless scalar or massless fields in 4 dimension, and then so you can get the massive free fields as a KK reduction. So you have some of the massive free scalars in the end. So what I'm doing is that the entanglement entropy in 3+1 dimension, but here in 4-dimensional case, I have an entanglement surface sigma times S1 because I extend 3-dimensional entanglement surface to 4 dimension. So in 4 dimension, entanglement surface is 2-dimensional. So since that's why I have sigma times S1 here as an entanglement surface. But this should be equal to the sum of the entanglement entropy in 3 dimensions, but with mass. So mass is actually, I erased this part. So mass is given by 2 pi m over L. This is KK mass. And I take a summation over n. Okay, so this should hold. So this is the entanglement entropy in 3+1 dimension. And this is 2+1 dimensional entanglement entropy, but with mass. And I will substitute this expression in the right-hand side and compare it with the 4-dimensional entanglement entropy. Okay. So this is my strategy. Okay, so, but in the left-hand side, so we have a log divergence because theory is in even dimensions. So we have log divergence. And, but on the other hand, in the right-hand side, we don't have any log divergence. But actually, so after summing over KK modes, so you see that there appears a log divergent term, so which comes from the first part. I mean, in the right-hand side, you have a summation over 1 over m, but here m is supposed to be linear in n. So somehow, yeah, after taking L goes to the infinity limit, then so you can replace this summation to the integral. But you have to have a UV cutoff in 4 dimension. So you cut out the higher momentum of higher modes, and then you will get the log divergence from the right-hand side. Okay, so what I'm saying is that, okay, from the right-hand side, so you have a summation over n, well, sorry, 1 over n, but you take a kind of continuous limit. So where you replace this summation by an integral over p, and p is basically proportional to n, but here you have to introduce the 4-dimensional UV cutoff. So this gives you some coefficient times c minus 1 sigma times log of epsilon. So you get the log divergence, whose coefficient is given by c minus 1. Okay, and from the left-hand side, so we have already know that there is a log divergence. So this is we have log divergence, and whose coefficient is given by A anomaly times the Euler density. Not Euler density, but Euler number. Euler number of sigma times S1, and plus C times. I think I didn't explicitly written down this part in my previous talk, but here, so you have an integral over the entanglement surface, sigma times S1, and here you have a, let's say, so this is kind of complicated, so I just schematically show that. So this is given by the four-dimensional extrinsic curvature. Extrinsic curvature is k, and k squared. You have some k squared term here, plus da da da. So this is a four-dimensional extrinsic curvature. Sorry, this is now two-dimensional extrinsic curvature. Extrinsic curvature again. Extrinsic curvature. And it depends on the shape of my entanglement surface. So sigma times S1. So then, okay, after evaluating this part and taking a reduction, then so you can fix the C minus 1 by comparing the log divergence part. So now C minus 1 is given by, okay, I only consider the free scalar and free fermion. Okay, times integral over sigma and times kappa squared. So this is a number of scalars. This is a number of scalars. And this is a number of fermion. Okay, so this is the final answer for free fields. So C minus 1 is given by some coefficient times the integral of kappa squared. So kappa is the extrinsic curvature of sigma, and this is even function as we expected. Okay, so we fix this coefficient by starting with four-dimensional field theory and take a KK reduction. And similarly, if you are interested in the subleading terms, then you can start with, okay, if you want to fix the next coefficient C minus 3, then you can start with 6-dimensional field theory and take a KK reduction to 3 dimension. And similarly, you can systematically compute these coefficients. Okay, at least for free fields. Yeah. Okay. Is there any questions? Okay. Anyway, so finally we fix this part. So let's apply this result to the renormalized entanglement entropy. Okay, so if you plug this expression into the definition of the renormalized entanglement entropy, so you see that okay, now I apply my result for a disk. So S1, sigma is now S1 of radius R. Then kappa is 1 over R. And if you plug this expression to the definition, then the renormalized entanglement entropy then turns out to be pi over mR. So this is the leading part. mR cubed. Okay, so this is the renormalized entanglement entropy for scalar. So this is for scalar field, for massive scalar. So you see that it is always positive and also monotonically decreasing